variational problem, the problem of finding a function y of x. So we are going to find out y of x, for which the functional I equal to integration x1 to x2 f of x comma y dash dx is extremum. Here extremum means maximum or minimum. Under the condition y of x1 equal to y1 and y of x2 equal to y2 is called variational problem or fundamental problem of calculus of variation. Observe, in these problems we are going to find out y of x. They will give one integration, that is integration x1 to x2 f of x comma y dash dx. To find out the integration constants, we are using the end conditions y of x1 equal to y1 and y of x2 equal to y2. So this problem is called variational problem or fundamental problem of calculus of variation. Euler's equation, a necessary condition for the integral I equal to integration x1 to x2 f of x comma y dash dx, where y of x1 equal to y1 and y of x2 equal to y2. To be an extremum is that dou f by dou y minus d by dx of dou f by dou y dash equal to 0. So that means this integral value will have maximum or minimum value when this condition is true. So now we are going to prove this condition. Let the curve y equal to y of x passing through 2 points. Here P is one point, Q is another point. Let the curve y equal to y of x passes through the points P of x1 y1 and Q of x2 y2. May I on an extremum. For the on this curve y will be extremum. Let y equal to y of x plus h into alpha of x, equation 1, be the neighboring curve joining the points P of x1 y1 and Q of x2 y2. So this is y equal to y of x. Above this curve there is one more curve y equal to y of x plus h into alpha of x. Both curves starting point is P and ending point is Q, such that alpha of x1 equal to 0 at P and alpha of x2 equal to 0 at Q. Observe, here alpha of x is there. This alpha value at x1 is 0. Alpha value at x2 equal to 0. When h equal to 0, these two curves coincide. That means here you can observe 0 into anything 0. Then at that time both curves equation becomes y equal to y of x. That's why when h equal to 0, these two curves coincides, thus making I an extremum. So observe, I equal to here x1 to x2 f of x comma, here we are substituting y value as y of x plus h into alpha of x and y dash value as differentiation of this y, that is y dash of x plus h into alpha dash of x dx is an extremum when h equal to 0. Clearly, here I is a function of h. Observe, here I is a function of h, and therefore the necessary condition for this function h to be extremum or stationary at h equal to 0 is di by dh equal to 0 for h equal to 0. This is we taken from differential calculus. Using Leibniz rule for differentiation and integral sign we have. Now we are going to differentiate this I with respect to h. That means I becomes di by dh. In the RHS also we are going to write d by dh and the remaining function as it is. By using Leibniz theorem, this integration goes into, this differentiation goes into integration as partial differentiation. That's why d by dh becomes dou by dou h. Remaining is as it is. Let y of x equal to y of x plus h into alpha of x implies y dash of capital letters are these are capital Y, this is capital Y dash. So di by dh equal to dou by dou h of f of x comma capital Y comma y dash dx. So we are taking integrand as outside. First of all, we want to find out integrand value. Dou f by dou h of x comma y dash. This is also by using, this is also we have chain rule in your first sem. That's why dou f, how we can write this means dou f dh, dou f dh, dou f dh. Here x is there, that's why dou x dx. Here y is there, dou y dy. Y dash is there, dou y dash dy dash. So completely we are going to get equation number 3. But when h equal to 0, capital Y equal to small y and y dash equal to small y dash, 0 into anything 0. So dou f by, at that time, dou f by dou capital Y equal to dou f by dou small y, dou f by dou capital Y dash equal to dou f by dou y dash. Since h is independent of x, we have, that means h does not containing any terms of x. We have d by dh of x equal to 0. So capital Y of x we already known. Now we are going to differentiate with respect to h. So y of x, this is no h term, that's why 0. Here keep alpha x as constant. For h1, 1 into alpha of x is alpha of x. Y dash of x equal to y dash of x plus h into alpha dash of x. Here y dash of x is constant, 0. Alpha dash of x is also constant, put aside for h1. So we are going to get alpha dash of x. Now we know all the values. We are going to replace all the values. First observe the equation number 3. LHS no change. Dou f by dou x as it is. This is 0 because h is independent of x. Plus this one is also as it is. Dy by dh is alpha of x. This one is also as it is. Dy dash by dh is alpha dash of x. So 0 into anything equal to 0. So we are going to get this expression. Now I am going to write this expression in integration. So separate integration. Here we observe dou f by dou y alpha of x dx, dou f by dou y dash integration x1 to x2 alpha dash of x dx minus so observe here we are going to write integration for both terms separately. We did not do any integration for the first term. We are doing integration for the second term, that is first function into integration of second one minus integration of differentiation of first one into integration of second one dx into dx. That means product rule of integration. So we are not doing any integration for first term. So first term will come like this as it is. So dou f by dou y dash like this only. Integration and differentiation cancel. We are going to get alpha of x. Here lower limit is x1, upper limit is x2. So here also integration and differentiation cancel. We are going to get alpha of x. So this term as it is into dx. Here we are going to substitute the limits alpha of x2 minus alpha of x1. But the value of alpha of x2 is 0, alpha of x1 is 0. 0 into anything is 0. So we are going to get only first term and third term. So we are going to get di by dh equal to, observe here integration from x1 to x2. Here also integration from x1 to x2. So we are going to write one time only. This is dy by dx, dou f by dou y. We write dou f by dou y here. D by dx of dou f by dou y dash here. Here alpha x is there, here alpha x is there. That's why we are putting alpha of x outside dx. So, but di by dh equal to 0 at h equal to 0 for I to be extremum. That's why the integrand in RHS must be 0. To get di by dh 0, if LHS equal to 0 means RHS is also 0. Whenever RHS becomes 0 means dou f by dou y minus d by dx of dou f by dou y dash equal to 0. So that is our Euler's equation.